Hello again and welcome to this video on the extended Euclidean algorithm. So in the last video we learned about the Euclidean algorithm and what it's for. Namely, it's a process that computes the greatest common divisor of two integers. Here on the screen I have the results of the first calculation we did in that video where we used the Euclidean algorithm to calculate the GCD of 888 and 54. That turned out to be 6, and importantly I want to look at the steps here. We started off by dividing 54 into 888 and found that it went 16 times with a remainder of 24. To continue the Euclidean algorithm, I shifted the 54 and the 24 into the previous spots for 888 and 54. So 54 is being divided into, and 24 is now the divisor. We can quickly check that 24 goes into that twice with a remainder of 6, and then I shift again and divide 6 into 24 and see that that goes in 4 times with a remainder of 0. Now the Euclidean algorithm says stop with the last non-zero remainder, that will be right here, and that's your GCD. So we're going to use this fact that 6 is the GCD of 888 and 54, as well as the results of the process, to do something interesting with this GCD. I'm going to draw a little line right here and work with the two equations you see above that line. Starting with the number 6 here. I claim that I can write 6 as a sort of combination of 888 and 54. Let me show you what I mean by that. So I'm going to start off by taking this equation and rewriting it in a slightly different form. I'm going to write this as 6 equals, I'm going to solve this equation for 6, basically. So 6 would equal 54 minus 24 times 2. Now certainly that's correct because 24 times 2 is 48 and 54 minus 48 is 6. I'm going to rewrite this just slightly one more step here, and instead of saying minus 54 times 2, I'm going to say plus 24 times negative 2. Now, interestingly, if I look up in the first line here, I see 24 hanging out in the remainder spot. Now I can solve that equation for 24, and 24 would be equal to 888 minus 54 times 16. And I'm going to put that into this equation over here where you see the number 24. Let me put this in green. So 24 I could also rewrite as 888 minus 54 times 16. And that was being multiplied by minus 2 from the line up above it. So basically what I've done is I've substituted 24 with something that it's equal to. Now let me simplify some of the math here and explain what happens. Okay, so I have 54 in here. Inside the parentheses, I'm going to do what I did a little earlier and say this is 888, and not subtracting 54, but adding 54 times a negative 16. And the whole group there is multiplied by minus 2. Now if I distributed that minus 2 through, what I'd have here, I have a 54 here, and I would have 888 times minus 2, and then I'd have to multiply it to here as well, so that would be 54 times negative 16 times negative 2 is positive 32. Now I have a 54 over here as well, so in the end I can write this as 54. How many 54s do I have? I have 1 here and 32 of them here, so that's 33 times, or plus 888 times minus 2. And this is all equal to 6. Now you can check that this is true, but importantly notice what I've done here is I started by looking, this whole process, I started by looking at 888 times and 54 and found that their GCD was equal to 6. Using the results of the Euclidean algorithm and sort of working backwards through the Euclidean algorithm by starting with that last non-zero remainder and successfully doing some solving and substitution, I've actually written 6 as a combination of 54 and 888. I can take 6 and write it as 54 times an integer plus 888 times another integer. This sort of construction right here is called a linear combination. Linear combination of those two numbers, 54 and 888. What I've done here in forming a linear combination of these two numbers is I've taken 54 and 88 and multiplied them by integers and then added them. That's what a linear combination is. And what I see here is that the GCD of those two numbers is actually equal to a linear combination of the numbers that gave me the GCD in the first place. This turns out to be true for every pair of positive integers you can find, that the GCD of two integers can always be written as a linear combination of those two integers. And the process that we just went through, this long process right here of finding the weights that I multiply, these two guys right here, is called the extended Euclidean algorithm. So I can use the Euclidean algorithm to find the GCD in the first place. That's what we did over here. And then if I wanted to, I can find I can use the extended Euclidean algorithm to write the GCD as a linear combination of the original two numbers. And for us, that's going to be actually a very important process. So let's do one more example. Actually, this is sort of a two-stage example. I'm going to look at the numbers 1180 and 482. And first of all, I'm going to use the Euclidean algorithm to find their GCD. When I do that, so this is another example of something we've already seen, but importantly, I need to keep track of the results here. So let's run through the Euclidean algorithm and see what happens. So the larger of the two numbers is 1180. So I'm going to try to write 1180 as 482 times something plus a remainder. This is basically long division, but I'm not going to write the long division out. If you wrote it out as long division, you'd find that 482 goes in twice with a remainder of 216. Now let's shift and see if I can find 482 equal to 216 times something plus another remainder. This remainder right here was not 0, of course, and so the Euclidean algorithm hasn't terminated yet. Now 216 goes into 482 twice with a remainder of 50, so I'm still not done. Let's shift them over. 216 is equal to 50 times something plus a remainder. I can see that that goes in 4 times with a remainder of 16. Still not a non-zero, still not a 0 remainder, so I need to keep dividing. If I take 50 and divide it by 16, that is going to go in 3 times with a remainder of 2. That's still not 0, so I've got, I think, one more step to do with the Euclidean algorithm. Shift again and see if I can divide 16 by 2, which of course I know how to do that. That's 8 with a remainder of 0. The Euclidean algorithm would say stop here and look at that non-zero remainder, that last non-zero remainder. That's the GCD. So these two numbers have a GCD of 2. So what we're going to do now is use the extended Euclidean algorithm to write 2, that GCD is circled in red there, as a linear combination of 1180 and 482. In other words, I'm going to try to find two integers such that 2 is equal to 1180 times one of them, plus 482 times something else. Now, how we're going to do that, again, is to start at the end of the Euclidean algorithm and work our way backwards. I'll do this in red. So let's first of all solve that last equation for 2. This is going to be 2 is equal to 50 minus 16 times 3, but I'm going to write that as plus 16 times negative 3. Again, I've just taken that last equation on the bottom there in blue and solved it for the number 2, the smaller number there. Now, if I work my way up the chain here, what I see is that 16 can be written as 216 minus 50 times 4. So I'm going to substitute this 16 right here with something that it's equal to. So this is 50 plus, I'm going to make a substitution that's going to equal 16. I'm already multiplying the 16 times a negative 3. So what goes in here, that is going to be 216 plus 50 times negative 4. Now let me distribute the 3 through, and notice what's going to happen here. I'm going to have 216 times negative 3, and then I'm going to have 50 times negative 4 times negative 3. That's 50 times 12, and I have another 50 hanging out over here. So in all, that becomes 50 plus, or 50 times 13. And if you stop right here and just computed this right-hand side, you would see that it equals 2, and it's a useful check. Okay, so now I notice that 50 right here can be written as 482 minus 216 times 2. And so I'm going to do a substitution here of the number 50 that you see right there. So I'm going to create a space for the substitution, keeping in mind that I'm already multiplying all that stuff by 13. Now, according to the second line of my Euclidean algorithm, 50 is equal to 482 plus 216 times negative 2. Now let's check things out here. I have 216 times negative 3, and I also have 216 times negative 2 times 13. So how many 216s is that in all? Well, I had negative 3 right here, and I'm going to have negative 26 right here. So this is a total of negative 29 times 216. And the 482 is also going to be multiplied by 13 once I distribute this 13 through the group. So you can stop right here and check that this equation, this side right here, does actually equal 2. Now, one last substitution step. Okay, the 216 here can be written as 1180 minus 482 times 2. So I'm going to do one last substitution, and then I think we'll be close to done. The 216 is equal to 1180 plus 482 times the negative 2. And this is all times negative 29. And this is also all plus 482 times 13. So now let's see where we end up here. If I distribute this negative 29 through, what I end up with here is I have 1180 times negative 29. And a lot of 482s. Negative 29 times negative 2 is 58. And I have that many 482s here. 58 plus 13 is 71. So this is 482 times 71. And now, if you notice, I've actually done what I set out to do. This 2 is now equal to a linear combination of 1180 and 482, and I know what the multiples are. This is going to be negative 29, and this is going to be 71. So that's what the extended Euclidean algorithm does. The Euclidean algorithm allows us to go from two numbers and end up with the GCD. The extended Euclidean algorithm starts at the end of the Euclidean algorithm, works its way backwards up through the Euclidean algorithm this way by making a series of substitutions with the goal of writing the GCD as a combination of the two numbers that generated the GCD in the first place. Now, why is that important? Stay tuned for the next video to find out.